Good morning, everyone. I'm Greg Kenyon. I'm an emulsion formulation supervisor at Suit-Kote, where I've worked for 9 seasons, the last 5 specializing in asphalt emulsions and the formulations of them. Thanks for all being here today, and a special thanks to PEMA for the opportunity to speak about asphalt emulsions up here. So, Emulsions 101, understanding asphalt emulsions, what we can of them. Agenda here, asphalt emulsions, why we use asphalt emulsions, some of the components in chemistry. I'll try not to go too far into the weeds here. How emulsions are made, types of asphalt emulsions, and some challenges, and then Q&A if anybody has any questions. Okay, so emulsions are in everybody's lives every day, but we're going to talk about asphalt emulsions. Other emulsions being some great things like ice cream or Italian dressing. We're basically taking 2 liquids that don't like to mix together, and we're mixing them, making a homogeneous liquid. So asphalt emulsions are a mixture of asphalt binder, water, and an emulsifying agent. You need the stable suspension of asphalt droplets in water, and all of this enables low temperature application compared to hot mix asphalt. It's used in road construction, maintenance, repair, and pavement preservation. And then in the slide here, we just have a sample of asphalt emulsion that's under a microscope showing nice even particle sizes, which indicate a nice stable emulsion. Why do we use asphalt emulsions? They're cost effective. They do extend your pavement life and reduce your long-term maintenance costs. They are environmentally friendly, a lot lower energy use and emissions compared to hot mix asphalt. They're very versatile, suitable for diverse applications. You name it, we could probably make an emulsion that'll do it. They're safer in comparison to using hot binder with a low temperature application. It's reducing burn risks and improving overall worker safety. Components of asphalt emulsions. So roughly 50 to 75% of emulsion is asphalt binder. This provides the binding and waterproofing that we're looking for to create and preserve roads. There's water that acts as a carrier, which enables that low temperature application. There's a lot of additives, modifiers for performance, polymers, stabilizers, thickeners, anti-strips. There's oil distillates for workability in your cold mix pavements, and for pen modification for ideal field performance. There's reactants being a strong base for anionic emulsions or a strong acid for cationic emulsions. How do we put emulsions together? So asphalt emulsion is manufactured by heating asphalt binder, preparing a soap solution with water, emulsifier, and neutralizing agents being a strong acid or a strong base, depending on whether or not you're working with anionics or cationics. You're combining them in a colloid mill with high shear rates to create a stable oil and water emulsion. And the chemistry in the soap or what goes into the water stabilizes particles and dictates performance. So basically anything you put into the water phase, that controls most of the way your emulsion is going to behave. And to simplify it, really, we're taking all the ingredients, we're putting it into a big blender, we're shearing the asphalt into microscopic particles, and you're making a nice brown asphalt emulsion. And that's kind of a very crude example there. How does emulsion stay together? So an emulsifier barrier, charged emulsifiers, anionic or cationic, coat the asphalt droplets, and they prevent breaking or coalescing or just the the asphalt droplets from coming back together. There's electrostatic repulsion, so like charged droplets repel each other, maintaining dispersion in water. Small, uniform droplets, usually 1 to 10 micrometers. The high shear milling creates tiny, consistent droplets, reducing the risk of aggregation or flocculation, or just the asphalt coming together before you want it to in tanks. The end result here is the emulsion remains stable until field application triggers intentional braking. In the pictures here, we sort of have an example of a colloid mill just by itself, and then down below, you can see there's 2 asphalt molecules, and around them are the emulsifier barrier. And based on what you put into your soap phase, you can change how long or how fast those asphalt droplets come together. So it could be a rapid set, medium set, slow set, quick set. Over here, it just shows you another example. Cationic emulsions, they're positively charged, and you can see the droplets there with the plus ions, and in the middle there is the water, and that's keeping your emulsion stable. So it's stabilizing those asphalt droplets into the water. And the anionics, the opposite. Negative charge made with a strong base, but they sort of are working the same way, and the asphalt droplets are repelling each other. Deciphering the code here. I have A for anionic, but in many cases, if you're looking at these types of oils, there won't be an A. It'll just be the absence of a C that'll designate anionics. C is always cationic. RS is rapid set. MS being medium set, SS being slow set, QS being quick set. A 1 designation is usually lower viscosity or lower asphalt content. A 2 being higher viscosity, higher asphalt content. H being a hard base, 40 to 90 penetration. HF being high flow, and then there's also P for polymer, L for latex. Those are all things you might see. Types of asphalt emulsions. We have rapid sets. I could go through all the ones on top and their designations, but I think I go past the half hour I've been given. These are typically used for surface treatments. So they're used on clean, uniform sized aggregate to bond the aggregate to an existing road substrate. Greater than 1% fines, or that number 200 sieve, so really the dust-like material, can greatly reduce the effectiveness of stone retention with these rapid sets. So what's going to happen with a rapid set is if you have too much dust on your stone, the oil is going to stick to the dust and not the stone, and obviously that's a problem where we see stone loss. We have medium sets used for dense cold mixes, open graded cold mixes, recycle mixes, surface treatments. Medium sets are a little bit more forgiving for dirtier aggregate, but obviously you're going to sacrifice your set time. So a medium set being a slower emulsion that'll give the emulsion time to penetrate that dust and stick to the stone. Medium sets are typically used to mix well-graded aggregates with low to moderate fines content, so 2 to 10% of the minus 200 sieve. This is capable of mixing, transporting, and applying mixes long distances and moderately extended durations of time. So you have your pug, and if you've got 45 minutes to drive down the road before you're paving it, it shouldn't be an issue. It's not going to come out in a cube out of the back of the dump truck. We have slow sets. These are typically used for in-place road profiles, in-place and pug mill recycle. Slow set slurry seal applications, say that 3 times fast. This has the ability to coat and mix aggregate blends of greater than the 12% number 200 sieve. This also gives you very thin film coatings due to low surface tension of the emulsion, but allows for more thorough coating of aggregates. So these slow sets are going to really help you with in-place train work. These grinders, they create a lot of dust. The slow set emulsions are going to sort of fight against all the surface area and the dust and still allow you to mix and pave. We have quick sets, typically formulated as cationic, such as used in slurry seal and microsurfacing, capable of mixing very high fines content up to 20% minus 200 sieve, which again is that really fine powdery stuff. Typically this will be traffic ready in 60 minutes. Slurry is dependent on mechanical break, so wind, temperature, and sun. Micro relies more on a chemical break, being the emulsifier, cement or lime additive, and the geology of the stone. You'll probably talk about a lot of tack coats later. They can be RSs, MSs, SSs, QSs. All of the above depends on what you want. A modifier for asphalt emulsions is high float. So high float's going to give you a gel-like structure that resists flow at higher temperatures. This must pass a float test of 1200 seconds in a 140-degree water bath, which is sort of to simulate the surface of the road on a hot day, so you're not seeing that asphalt bleed up through. Again, less prone to bleeding with high temperature resistance, and it gives you thicker film coatings. And if you look at the pictures down here, the sample containers have the same asphalt on both sides, just one of them has high float chemistry introduced into it, and you can see what happens over the course of 8 hours. We can modify emulsions with latex or polymer. They exhibit stronger, more elastic properties in the binder residue. That gives you better stone retention from the polymer or latex. This continues to reduce water susceptibility. This reduces flushing as compared to conventional emulsion. Polymers and latexes can be incorporated into basically any type of emulsion, so rapid set, medium set, slow set, quick set. Both latexes and polymers exhibit very high elastic recoveries and good softening points. Next, we have some of the challenges of asphalt emulsions. On the manufacturing side, this requires precise control of the ratios, temperatures, and emulsifier neutralization. One of the big risks is not totally being calibrated, and contamination. So if our pumps and meters aren't exactly where they need to be, you don't know exactly what's going into your final product, and it's not going to test out correctly. So we have to be on top of that constantly. Contamination, whether it be in the plant or during transport. So if you have a trailer that had SS1 on it, and then the next day you're hauling RS2 to a job, and that trailer wasn't empty all the way, you mix those two and you're not really going to have an RS or an SS. It's probably going to be somewhere in the middle and likely out of spec, and everybody's unhappy because you're not going to see the set time that you were expecting. Another challenge is weather sensitivity. We can't use this stuff in the rain typically. It'll wash off the road. Nobody likes that. Storage and handling, you don't want to freeze it, you don't want to overheat it. Storing emulsions outside the recommended temperature range can destabilize them and cause them to flip. Basically the asphalt and the water. You'll have asphalt at the bottom of the tank and water on top. Nobody wants to deal with that. Another thing, one of the challenges is performance variability. So for PennDOT, RS2 has a demulsibility spec, which is a 60 minimum with no maximum. So if you have one supplier who's in between 60 and 70 demulsibility, your set time could be, closer to an hour. If you have someone who's in the 90s for demulsibility, your set time could be 10 minutes or less. So that does make a big difference in your quality, but it's all passing oil. So it's just something to consider when you're looking at test results and things like that. With that, that was my last slide. Does anybody have any questions?
Great, thank you very much.
Thank you, everyone.